Students, in the previous video, we discussed how to convert a continuous AWGN channel into a vector channel. And the received signal x of t is not only a transmitted signal si of t, rather it is the sum of the transmitted signal si of t and additive white Gaussian noise process w of t. And here in this video, let us discuss how to characterize the output of the correlator, which is basically a random variable. Let xj be the random variable whose sample value is xj. We are considering only sample value of xj since the output of correlator is random one. And the output of the jth correlator is considered as xj when the input is received signal x of t. And this xj is completely characterized by the three statistical parameters which you are already familiar. You might have studied in a statistical subject as well as somewhere in the mathematics. They are mean, variance, and covariance. Let wj denote a random variable similar to the xj, which is a random variable when the input signal is x of t. And the sample value of this random variable wj is denoted by small wj, which is produced at the jth correlator in response to the channel noise w of t. It is very simple. You will get xj at the output of correlator when the input is x of t. Similarly, you will get at the output of jth correlator wj when the input is the channel noise wt. And the output of jth correlator xj, now we have to analyze these three statistical parameters. They are, the first one is mean. So here we'll discuss what is the mean of the random variable xj. And mathematically, the mean of any random variable xj is defined in terms of its expected value, that is the expectation of xj. And we know that the received signal x of t in its vector form is given by sij plus wj. So it is the expectation of sij plus wj, where sij is the vector representation of transmitted signal s of t and wj is the vector representation of random noise, that is w of t. And we know that the additive white Gaussian noise is characterized by zero mean, means it has zero mean, and its power spectral density is given by n0 by 2. So the expectation of this one is given by expectation of sij plus the expectation of wj. And this sij is a constant value, and the mean or expectation of the constant value is always the constant. Therefore, the expectation of Sij is equal to Sij, and the mean of this random noise signal Wj is always 0. Therefore, the mean of the random variable Xj is always equal to simply the Sij, which is a vector representation of transmitted signal Sij. And the second parameter we have is a variance of xj, which is denoted by sigma xj square, or simply variance of xj. And mathematically it is defined by expectation of xj minus mean of random variable, that is mu xj square. So the squared difference between xj minus mu xj. Xj is the random variable and mu xj is the mean of this random variable. And we know that from the previous parameter, that is the mean of random variable is equal to Sij. So this becomes xj minus Sij whole square. And we know that random variable xj with respect to the received signal x of t, which is xj is equal to Sij plus wj, and xj minus Sij is nothing but wj. So this step can be rewritten in the next step, that is E is equal to E of expectation of wj square. And this Wj is the output of jth correlator when the input is the random process W of t, and mathematically it is given by integration of 0 to t W of t pi j of t into dt. Since this sigma xj square is equal to expectation of wj square, it can be written as expectation of wj into wj. So it is the inner product of wj with itself, and here sigma xj square is equal to expectation. The first wj is nothing but 0 to t w of t pi j of t into dt, and another wj, just to distinguish between the two integration terms, I will consider another argument or parameter, that is u. So the second wj can be defined as integration 0 to t w of u into pi j of u into du. So here let us combine both the integration together with a basis function pi j of t and pi j of u. Then write the two the random noise random process with respect to different the arguments wt as well as wu with respect to dt and du. So now let us interchange the expectation as well as the integration. So first we'll take integration terms along with this basis functions, and then we'll take the expectation of this w of t and w of u. Then it is integration with respect to dt and du. And we know that the expectation of the random process w of t with respect to two different arguments, which is considered as the autocorrelation of wt, and mathematically it is denoted as rw of t comma u. R is autocorrelation of the random noise signal w with respect to two arguments t comma u, and its value is n naught by 2, because the power spectral density and this autocorrelation function, they are Fourier transformable pairs. Both they have the same content, that is n naught by 2 delta of t minus u. Means this power spectral density or n naught by 2 is defined only at delta of t minus u. So you let us substitute this n naught by 2 delta of t minus u in this equation. So sigma xj square is equal to, let us take this constant n naught by 2 outside the integration, keep the two integration as it is, along with pi j of t and pi j of u, and a delta of t minus u dt into d. So let us, to make this equation more simpler, let us consider t is equal to u, and when you consider t is equal to u, this becomes a delta of t minus t, that is delta of 0, and delta of 0 is defined as 1. And here pi j of t and this pi j of u, because we consider t is equal to u, both the basis function becomes similar, pi j of t and pi j of t. So that is pi j of t square, and when you integrate this pi j of t square over 0 to t interval, you will get 1, because according to the condition or properties of the basis function, so pi j of t have unit energy, and that energy is given by this equation, and this is equal to 1. Finally you will get sigma xj square, that is variance of xj, is equal to n naught by 2 for all the values of j. And here you can make an important note, the variance of the random variable xj is equal to the power spectral density of white noise, that is wt, given by n naught by 2. So hope you understood both the parameters, the mean as well as variance. And the third important parameter is covariance. Means here we are comparing the variance of two different random variables. They are namely xj and xk. They are the outputs of two correlators, jth and kth correlators. And the covariance means the similarity between the variance between these two random variables. So covariance of xa and xa is given by mathematically the expectation of the variance between the two random variables. The variance of the first random variable xa is given by xa comma minus mu xj, and the variance of the second variable xk is given by xk minus mu xk, where xa and xk are random variables and mu xj, mu xk are the mean values of these two random variables. And from the first parameter, that is mean of any random variable, is equal to the signal vector of transmitted signal Si of t. So Xa is equal to Sij and mu Xk is equal to Sik. And we know that Xa is equal to Sij plus Wj. So Xa minus Sij can be given by simply Wj. So it is Wj, and from this term it is Wk. And we know that the output of each correlator, either it is jth correlator or kth correlator, it can be defined by using equation 0 to t integration from 0 to t w of t pi j of t dt. And for this wk is 0 to t w of u. Here again, just to distinguish between these two integration and to avoid the confusion, we considered a different variable u for this wk. So that is w of u and pi k of u du. So again, combine both the integration along with these basis functions, that is pi j of t and pi k of u, and take the expectation of w of t as well as w of u and integrate the whole thing with respect to dt and du. And the expectation of this wt and wt is given by rw t comma u, which is basically a autocorrelation function, which is given by n naught by 2 delta of t minus u. And this one will substitute in this equation. So you will get n naught by 2, since it is a constant, it is taken outside the integration, and inside the integration we have two different basis function, then which is multiplied by a delta function at t minus u. And when you consider again at t is equal to u, the delta of t minus u becomes 1, and the remaining term will be n naught by 2 0 to t integration pi j of t and pi k of t dt. And here, this inside the integration, you can observe these two basis functions, they are not identical, they are different, because here the subscript what we have is, here we have j and here we have k, even though the function arguments are similar in both the function, that is t, and here also it is t. Since they are different basis functions and if they are mutually uncorrelated, we can we can conclude the integration over 0 to t between two different basis function gives 0. So this is the condition called as what? Orthogonality condition of basis function. And this integration, the product, the integrated product is 0. 0 into n naught by 2 gives 0. So we can conclude here the covariance between two different random variables, they are the outputs of jth and kth correlator, is equal to 0. So this is about the statistical characterization of the random variable xj with respect to mean, variance and covariance.